All right, so this is the Exam 4 review solutions for Math 95E. So part 1 asks us to simplify the following expressions. Now, it's not mentioned, but for any one involving variables, we want to make sure that we have only positive exponents. So if we ever have a negative exponent, we want to use the rule to make it into a positive exponent. So question 1 says negative x squared y squared z raised to the third power times 2x squared y cubed z to the fourth raised to the second power, or squared. Now, just as a reminder, this is a negative x. That's the same thing as a negative 1x squared y squared z. So, using the properties that we know, this first one is negative 1 to the third power, then x squared to the third power, then y squared to the third power, and then z to the third power. And similarly, for the other one, we've got 2 squared times x squared squared times y cubed squared times z to the fourth squared. Now, if you want to skip this step, you're more than welcome to. I'm just trying to show every detail. So, just to remember this part right here, this was this expression, and then this part right here was this expression. So negative 1 cubed is, of course, negative 1. And then x squared raised to the third power, whenever you have a power raised to a power, you multiply the exponents. So 2 times 3, that'll give us x to the sixth power. So this will be negative 1 times x to the sixth. Then it'll also be y to the sixth. And then for z to the third, z raised to the third power, remember there's just a hidden 1 there. So this just becomes z cubed. And on to the second set of terms. 2 squared, that's 4. X squared raised to the second power, x squared squared, is going to be x to the 2 times 2, or x to the fourth. Y to the third raised to the second power, that's going to be, once again, multiplication of the exponents. So we're going to have y to the sixth. And then z to the fourth raised to the second power, it's going to be 4 times 2, so z to the eighth. At this point, now that we've kind of simplified each of these two expressions right here, now we can start adding them together. So we have this negative 1 and this 4 that are being multiplied, so our coefficient is going to be negative 4. And then we've got an x to the sixth and an x to the fourth. When you're multiplying things, then you're going to add their exponents. So this will be x to the sixth plus 4, so that'll be x to the 10th. And then y to the sixth times y to the sixth, that's going to be y to the 12th, because it's going to be 6 plus 6. And then last, it's going to be z to the 11th, because it's going to be it's going to be z to the 3 plus 11. So just adding a little bit of a note here. So it's x to the 10th, because it's going to be that x to the 6th times x to the 4th is x to the 6th plus 4, which is x to the 10th. And the same thing for y and for z. So on to question 2, which is 3 to the negative 4 times 3 to the negative 9. Now, there's a couple ways you could do this. The way I would go about it is, because these two things have the same base, they're both base 3, and they're being multiplied, you can add their exponents. So this is this is 3 to the negative 4 plus negative 9, or 3 to the negative 13. But remember, 3 to the negative 13, we want to deal with positive exponents, so this is the same thing as 1 over 3 to the 13th. And you can leave it like that. If you want to actually write down what 3 to the 13th is, you could also write this as 1 over 159,4,323. So 1,594,323. Either way would be accepted on the exam. Just make sure that you're dealing with a positive exponent. Then we're going to go on to question 3. Question 3 says 2 raised to the negative 2, x to the third, y to the negative third, and then negative 2. Now, just like with any of these, really, there are so many ways to go about it. Me personally, I would like to distribute in, I'm loosely using the word distribute, but I'd like to take care of this negative exponent and bring it into all the factors here. But if you want to mess around with the inside first, you're more than welcome to. So what I'm going to do is this is going to be 2 to the negative 2 raised to the negative 2 times x to the third raised to the negative 2, and then y to the negative 3 raised to the negative 2. So, and remember, if you have a power raised to a power, you're going to multiply the exponents. So this is going to be 2 to the positive 4, because negative 2 times negative 2 is positive 4. Then it's going to be times x to the negative 6, and then it's going to be y raised to the positive 6. Now, it didn't really mention it in part 1, but as I mentioned earlier in question 1, we want to make sure we always have positive exponents. So this guy right here, this x to the negative 6, we want to write him as 1 over x to the 6th. So this right here is 1 over x to the 6th. So this is 16 times 1 over x to the 6th times y to the 6th, or preferably 16y to the 6th over x to the 6th. And that is our answer. Question 4. This is one of those ones that has a lot of ways that you can go about it. It's in parentheses 7x to the negative 2, y to the third, z to the fifth, all over 14 x squared, y to the fourth, z to the negative 3, all raised to the negative 2. As I said, there are so many ways you could do this one. Arguably, I just like to distribute in the exponent most of the times. However, I do see this 7 and this 14. When I distribute in this negative 2, these are just going to become bigger numbers and it's going to become more confusing. So off the bat, I'm just going to notice that 7 and 14 have a common factor, and the fact is that 7 and 14 cancel a little bit. So we're left with a 1 up top and a 2 down in bottom. So rewriting this just a little bit, this is going to be 1 over 1, or just x to the negative 2, y to the third, z to the fifth, all over 2x squared, y to the fourth, z to the negative 3, all raised to the negative 2. Now, Alex sometimes suggests that you take this negative exponent and flip everything. So bring the 2x squared y to the fourth, z to the negative 3 up top, and the x squared y cubed z to the fifth down to the bottom, and that takes care of that negative in front of the negative 2 exponent. But I like personally to just distribute it into every piece first, so I'm just going to take this and bring it into all the exponents. So this will be x to the negative 2 raised to the negative 2, y to the third raised to the negative 2, z to the fifth raised to the negative 2, and then 2 raised to the negative 2, x squared raised to the negative 2, y to the fourth raised to the negative 2, and z to the negative third raised to the negative 2. Once again, if you want to skip this step and just go ahead and multiply the exponents, you are more than welcome to do so. In fact, I encourage it. It's going to save you more time, and you probably should do that if this type of problem does show up on the exam. So, next step, this will be x to the positive 4, y to the negative 6, z to the negative 10, all over 2 to the negative 2, that's 1/4. And I'm going to write a little note as to y right here. 2 raised to the negative 2, that's 1 over 2 squared, which is 1/4. So that's where the 1/4 is coming from. Then it's going to be x to the negative 4, y to the negative 8, and z to the positive 6. So this isn't simplified, of course, because we can still deal with these x to the fourth and x to the negative fourth. Just as a note, these are not going to cancel. So we need to be careful there, and same thing here and here. And then, as a reminder, this is 1/4, but it's in the denominator, and whenever you're dividing by a fraction, you flip and multiply. So this is going to be 4, and then whenever you've got the same base, one up top and one on bottom, so I've got x to the 4 and x to the negative 4, it's always the top exponent minus the bottom exponent, regardless of whether the bottom exponent is positive or negative. So this is going to be x to the 4 minus negative 4, and then it's going to be y to the negative 6 minus negative 8, and then it's going to be z to the negative 10 minus 6. So that will be 4x to the 8th, y to the second power, because remember it's going to be negative 6 minus negative 8, so that's really negative 6 plus 8, so y squared, and then z to the negative 16. So, but the z has a negative exponent right here, so we want to make sure we take care of that, and that's going to be 4x to the 8th y squared over z to the 16th. So that was a mouthful, and I actually would like to do one more version of it, like the same problem, but show you a different way to do it so that you can see that there are multiple ways to do everything. So, to try it a different way, number 4, that's going to be, once again, we have, in parentheses, 7x to the negative 2, y to the 3rd, z to the 5th, over 14 x squared y to the 4th z to the negative 3rd, all raised to the negative 2. An alternate way to do this one would be to simplify everything, like combine everything on the inside first, and then work your way out, and then take care of this negative 2. So, once again, we see here that these are going to cancel just a little bit. And then remember, it's always with same bases, so this is x to the negative 2, this is x to the positive 2. You always do top exponent minus the bottom exponent. So this is going to be 1/2, and then it's going to be x to the negative 2 minus 2 times y to the 3 minus 4, and then z to the 5 minus negative 3. But don't forget about that outside exponent. That's still there. We haven't taken care of that. So simplifying the inside again, this is going to be 1/2, and then x to the negative 4, and then y to the negative 1, and z to the positive 8, all raised to the negative 2. Now I'm going to go ahead and take care of this this negative 2 exponent out here by bringing it into everything. Remember, it also has to go into this 1/2. So we've got 1/2 raised to the negative 2, and then x to the negative 4 raised to the negative 2, y to the negative 1 raised to the negative 2, and z to the 8 raised to the negative 2. So, taking care of this, just because it's going to be a little bit weird with that fraction, 1/2 raised to the negative 2, that's 1 over 1/2 squared. And 1/2 squared is 1/4, so this is really 1 over 1/4. And then remembering, if you're dividing by a fraction, you flip and multiply, so this is really just 4. So we end up with 4 times x to the positive 8, y to the second power, and z to the negative 16, which ends up being the same thing that I got before. This will be 4x to the 8th, y squared over z to the 16th. And that's, once again, because z to the negative 16 is 1 over z to the 16. That's an alternate way to do the same problem. Some people suggest flipping everything, as I mentioned previously, from the start, and then work your way from there. But there are so many different ways. So on to question 5. Question 5 is 3x squared plus 5y cubed raised to the 0. Now, as we know, there's the property about the exponent 0, so that anything raised to the 0, except for 0, is going to be equal to 1. So this is really just 1. Plain and simple. Anything raised to the 0 is equal to 1, save for the case we got 0 to the 0. That's an interesting case, but that's for another time. That's question 5. Question 6 also has to deal with the exponent 0. We've got negative 5 raised to the 0 plus 7 raised to the 0. Now, negative 5, oh, oops, sorry about that. Negative 5 raised to the 0, this is just going to be 1. Because anything raised to the 0 is 1, save for 0. And then 7 raised to the 0, that's also 1. So really, this expression is just 1 plus 1, which is 2. And there you have it. Question 7 is negative, in parentheses, 4 raised to the 0 minus 10 raised to the 0. Now we have to be careful here. Notice that this negative sign is in front of the 4. It's not included on the inside. So that is treated separately. So negative 4 raised to the 0, that's just equal to 1, but we still have this minus sign right there. So that's going to be this entire expression right here. This is equal to negative 1. So negative parentheses 4 raised to the 0 is actually equal to negative 1. And then similarly, well, not necessarily similarly, 10 to the 0 is just 1. So what we have here is negative 1 minus 1, which is negative 2. And now we move on to questions 8 and 9, which deal with scientific notation. So as remember, scientific notation is always a number, and the number needs to be between 1.00000 and 9.99999. So it can't be 10, it can't be 22. It has to be a number that's like a single digit point something, and then times 10 raised to a power. And the power could be positive or negative on the 10. So with question 8, we have 7 times 10 to the third power times 3 times 10 to the fifth power. Now when you're multiplying two numbers in scientific notation, what you end up doing is you take these two numbers and you multiply them together, and then you add the exponents. So what this is going to be is 7 times 3, and then times 10 raised to the 3 plus 5. That's going to be 21 times 10 to the 8th. However, we've got an issue here. In order for a number to be in scientific notation, the number needs to be between 1 and 9. So since this is 21, we've got an issue. So what we have to do is we have to mess around with it. So we're going to bring the decimal point over here, one more point to the left. So we're going to make it into a 2.1. However, we can't just make the number smaller and keep the same exponent. We can't keep the 10 to the 8th. We made 21 into 2.1. So we made this number smaller, which means in order to counteract that, we need to make this exponent bigger. So we're going to have to add 1 to the exponent. So this is really 2.1 times 10 to the 9th. In order for this to truly be in scientific notation, we need to take care of this issue. So remember, it's all a balancing act. So if you if you make the number here smaller, like I did, I went from 21 to 2.1. I moved the decimal place one place over, so I made it from a bigger number to a smaller number. So I need to make the exponent bigger to counteract it. And since I only moved it one place over, I have to raise it up one more point. So that's why it's 10 to the 9th. Then on to question 9. Question 9 is 15 times 10 to the negative 5 over 3 times 10 to the negative 9. Now, in a very, very similar fashion, with division and numbers in scientific notation, you take these two numbers and you divide these, and then you're going to subtract the exponents on the tens. It's always going to be top minus bottom. So this is going to be 15 over 3 times 10 raised to the negative 5 minus negative 9. So remember, you got to keep that minus sign that I've got here, because it's top minus bottom. Regardless of whether or not the exponents are positive or negative, that doesn't matter. It's always top minus bottom for these exponents. So 15 divided by 3, that's 5, and then it's going to be times 10. Negative 5 minus negative 9 is positive 4. And this number is already in scientific notation because 5 is between 1 and 9.9-ish. So had this been had this 5 been a 50 or a 0.5, then we have a little bit of an issue, and we'd have to mess around with it. But the number is already in scientific notation, and we're done there. And that concludes part 1. Part 2 has to deal with performing the indicated operations, so addition, subtraction, and multiplication, and division of a bunch of algebraic expressions. So, we're going to go ahead and start off with question 10, which is, in parentheses, 2x squared minus 4x, plus in parentheses, 3x squared plus 2x. Now, since these are being added together, we can just drop these parentheses and write this as 2x squared, sorry, my pen kind of a little weird there, minus 4x plus 3x squared plus 2x. And now we got to look for like terms. So luckily we've got this 2x squared and this 3x squared. Those guys can combine, and then this minus 4x and this plus 2x can combine. So we end up with 5x squared minus 2x. So for question 11, we have 5y cubed minus 3y squared minus, in parentheses, 2y cubed plus 8y squared. So remember, this minus sign here needs to get distributed into both terms of the second pairing right here. So whenever you got this minus sign, a very common mistake that students will make is they'll just distribute the minus sign into the first term, but they'll forget to put it into the second term. So I don't want you guys to fall for that. Remember, you got to distribute it into both. So this ends up being 5y cubed minus 3y squared minus 2y cubed minus 8y squared. And once again, we're looking for like terms, and we have some there and here. So this will end up being 3y cubed minus 11y squared. Then with number 12, we've got, in parentheses, 8m squared minus 7m minus, in parentheses, 3m squared plus 7m minus 6. And just like in the previous one, just like in question 11, this minus sign needs to get distributed into all three pieces. So I'm going to write this minus sign. I'm going to make sure I distribute it into all three pieces. So this will become the 8m squared minus 7m, that didn't have a minus sign in front of it, so we can just leave it by itself. But then it's going to become minus 3m squared minus 7m, and then plus 6, because that minus sign changed it from a minus 6 here into a positive 6. Now we look for like terms. Does 8m squared have any like terms? Yes, the minus 3m squared. And then the negative 7m? Yes, it has a negative 7m. But the 6, no like terms. He has no buddies, so he's just going to be left, he or she is going to be left by themselves. So, a very common mistake I want to mention before we move on, this minus 7m and minus 7m, they don't cancel. These have the same sign, so when we combine them, we're going to get minus 14m, or negative 14m. So this is going to be 5m squared minus 14m plus 6. So on to number 13. So number 13 is 3pr to the fifth minus 8pr to the fifth plus pr to the fifth plus 2pr to the fifth. The good news here is that like all these terms are like terms. But remember, you have to make sure that they have the exact same variables to the exact same parts. So starting with 3pr to the fifth, this is also a like term, this is also a like term, and this is also a like term. So we can combine all these ones. So that should be, remember there's a hidden 1 right here. So what we end up with, so 3 minus 8 plus 1 plus 2 ends up being negative 2pr to the fifth. 14. Now I'm going to write this one out. This one says subtract 18y to the fourth minus 5y squared plus y from 7y to the fourth plus 3y squared plus 2y. So we need to be careful here. The verbiage is very important. It's saying we're going to subtract this term, 18y to the fourth minus 5y squared plus y, from 7y to the fourth plus 3y squared plus 2y. So this is the same thing as 7y to the fourth plus 3y squared plus 2y minus, in parentheses, 18y to the fourth minus 5y squared plus y. The second thing, the 18y to the fourth minus 5y squared plus y, that needs to be in parentheses because we're subtracting that entire thing. If I were to get rid of those, then it would only be subtracting the 18. It wouldn't be doing what we want it to do. So we need to make sure we distribute this minus sign into all three terms, and what we end up with is 7y to the fourth plus 3y squared plus 2y minus 18y to the fourth plus 5y squared minus y, because the minus sign right here, that changes the sign of every term in this expression, this set of three terms. So starting with the 7y to the fourth, we're going to look for what like terms, and there's the 18y to the fourth. Then we'll move on. The 3y squared has the plus 5y squared, and last but not least, the 2y and the minus y, or minus 1y, are like terms. So combining these things together, we've got negative 11y to the fourth plus 8y squared plus y. And that is our answer. And on to 15. 15 is 2m times 2m plus 3. So there's a little multiplication here. So we've got to take this 2m and distribute it in. Now this first time I'm going to show the whole work for it, but in the future it's better if you get quicker at these types of things. So this is going to be 2m times 2m plus 2m times 3, which is 4m squared plus 6m. And if you want to go straight from this to the answer, you're more than welcome to. You'll get full credit for this. So you just need to make sure you distribute the 2m into both terms, and then so the 2m times the 2m, that's 4. Like the 2 times 2 is 4, and then 2m's multiplied together gives you m squared, and then similarly for the 6m. 16 is y to the fifth times 9y times y to the fourth. So there's a lot of, like, if you feel comfortable writing out writing the answer right away, go right ahead, but I'm going to do a little extra and then say this is, the only coefficient is this 9, so that's there, and then we have y to the 5, and then remember there's a hidden 1 on this y term in the middle. It's hidden 1, so then it's going to be 5 plus 1, wrong color, plus 1 plus 4, which is 9y to the 10th. And because that's a positive exponent, we're happy with it and we can leave it alone. 17 is very similar to 15, just a little extra added work on top. 2m to the fourth times 6 plus 5m plus 3m squared. So once again, we're going to take this 2m to the fourth and distribute it into all three pieces. 2m to the fourth distributed into the 6 will give us a plus 12, or positive 12. Positive 12m to the fourth. Distributing the 2m to the fourth into the 5m will give us a positive, so plus 10m to the fifth. And then distributing the 2m to the fourth into the 3m squared will give us a plus 6m to the sixth. 18. We've got 6x plus 1 times 2x squared plus 4x plus 1. So this is a situation, this is not a, like in 17 we had a monomial here, we had 2m to the fourth being distributed in. here we've got a binomial, so we've got two terms that need to be distributed in, so we have to do our foiling technique. So we're going to have to take the 6x and we're going to have to distribute it into all three pieces of the second term, and then we're going to take the 1 and distribute it also into all three pieces. And so I'm going to write these in color. So this is going to be, when I distribute the 6x into the 2x squared, I'm going to get a positive 12x cubed, and then I'm going to get a plus 24x squared, and then I'm going to get a plus 6x. Now moving on to the 1 and distributing in, luckily 1 times anything is itself, so this is going to be a positive 2x squared plus 4x, and then 1 times 1, that's plus 1. So now we got to look for like terms. So the 2x cubed, no like terms. The 24x squared, oh, there's a 2x squared that can be combined. And then the 6x and the 4x are like terms. And then last but not least, the 1 is by itself. So we're going to combine these things. The 12x cubed is by itself, so it stays 12x cubed. 24x squared plus 2x squared is 26x squared, so we have plus 26x squared. 6x plus 4x, that's positive 10x, so plus 10x. And then we still just have that plus 1. 19 is m plus 7 times m plus 5. And so once again, we've got to do our foiling. So we're going to have to take the m from the first term and distribute it into both terms of the second. And then take the 7 and distribute it in as well, the two terms. And this time I'm not going to use color, but you're going to get m times m, which is m squared. And then m times 5, that's positive 5m, so plus 5m. 7 times m, that's positive 7m, or plus 7m. And then 7 times 5, that's plus 35. And so the only like terms that we see here are the positive 5m and the positive 7m. So combining like terms, we end up with m squared plus 12m plus 35. Number 20 is x plus 5 times x minus 5. Now, if you heard the terminology, this is actually what we call a difference of squares. So if you know about differences of squares, you can immediately write the answer, but it's totally fine to just go ahead and FOIL like normal. And what you'll end up with is x squared when you multiply the x times the x, and then minus 5x. And then when I do 5 times x, I'll get positive 5x or plus 5x. And then last but not least, 5 times negative 5, that's negative 25 or minus 25. Looking at the like terms, we have this negative 5x and this positive 5x, which will combine to equal 0. So that just goes away, and we end up with just an x squared minus 25. 21 is 5a plus 1 times 2a plus 7. Once again, got a FOIL. And 5a times 2a, that's 10a squared. 5i times 7, that's positive 35a. 1 times 2a, that's positive 2a or plus 2a. And then 1 times 7, that's plus 7. And we have these like terms that can be combined, and we've got 10a squared plus 37a plus 7. And that is our answer. 22 is b plus 8 times 6b minus 2. And it's the same old thing, distribute the first set by into the second set by foiling. So b times 6b is 6b squared. b times negative 2 is minus 2b. 8 times 6b, that's plus 48b. And then 8 times negative 2, that's negative 16 or minus 16. And then we've got our like terms right here and here. So this will be 6b squared plus 46b minus 16. On to 23. So 23 is 3t minus 4s times t plus 3s. So this is the first time we've seen two different variables involved in an expression, and that's okay. It's not a big deal. We're still going to distribute like normal. We're going to FOIL like normal. 3t times t is 3t squared. 3t times 3s is positive 9ts, so plus 9ts. Then negative 4s distributed into the t gives us negative 4st, so we've got a minus 4st. And then negative 4s into 3s, that'll give us negative 12s squared. Now you might think at the start that there are no like terms. However, multiplication is commutative, so like a times b is the same thing as b times a, or like 3 times 5 is the same thing as 5 times 3. So this right here is the same thing as negative 4ts. Or you could write the other one, you could write this as 9st, however you want to do it. But just because that's the way I decided to do it, we've got 3t squared and plus 5ts, because 9ts and negative 4st are like terms. They have the exact same variable pieces to the exact same powers. And then we have that minus 12s squared. And that is our answer. 24. Now this is a very classic one that students make mistakes on. X plus 7 squared. Now notice that this very classic mistake is just to square the x and square the 7, and that's it. But that's not correct. What does this mean? This means that we're going to take this expression and multiply it by itself 2 times. So we've got, this is the same thing as x plus 7 times x plus 7. So we have to distribute. So distributing it in, FOILing, we're going to get x squared plus 7x, and then plus 7x plus 7 times 7, that's 49. And that'll be x squared plus 14x plus 49 because of these like terms here. And that is our answer. So yes, please don't make the mistake that many students do. It's not x squared plus 49. You have to FOIL. You have to rewrite it out as x plus 7 times x plus 7 and FOIL. 25, very similar, 2z minus 5y squared. That is 2z minus 5y times 2z minus 5y. And so what we have to do is we have to distribute, or we have to FOIL. And we end up with 2z times 2z, that's 4z squared. Z squared. And then 2z times negative 5y, that's negative 10zy. And then negative 5y times 2z, that's negative 10yz. And then negative 5y times negative 5y, that's positive 25y squared. The negatives cancel out. And as a reminder, just like in 23 up above, we can rearrange the terms to make this look right. This is the same thing as negative 10zy. Or you could have written this first term as negative 10yz. Doesn't matter. And we can combine these like terms then, and we end up with 4z squared minus 20zy plus 25y squared. And I know the answer key says negative 20yz, but it's the same thing because multiplication is once again commutative. So yz and zy are the same thing. 26. You've got 2/3 plus r times 2/3 minus r. And once again, this is a difference of squares, so if you know how to do the difference of squares, go right ahead. But it's totally fine to go ahead and FOIL. 2/3 times 2/3 is equal to 4/9, and I'm going to do that off on the side here. 2/3 times 2/3. You multiply across, and nothing can cancel diagonally or vertically, so you just get 4/9. That's where I'm getting that 4/9. Then we have 2/3 times negative r, that's minus 2/3 r. R times positive 2/3, that's going to be plus 2/3 r. And then r times negative r is minus r squared. And luckily for us, these two things are like terms, and because they're the exact same term, but one's positive and one's negative, these completely cancel, and we end up with just 4/9 minus r squared. It's just throwing in fractions there to try and scare you, but fractions are no different than any other number. All right. 27 is p times 3p plus 7 times 3p minus 7. Now this is a product of three different polynomials, and so we get our choice of which ones we want to multiply first. We could either first distribute the p into the first set, or we could even do it into the second set if we wanted to, but that's unnecessary, or we could take care of this foiling situation first. I'm going to opt to distribute the p in first, but you can definitely go ahead and try doing it by foiling first and then distributing in the p and see what you get. But me, first, I'm going to take care of this, distribute that in, and what I've got is 3p squared plus 7p times 3p squared minus 7. It's not p squared, excuse me, just 3p. So now I've got to foil this in, and what I'll end up with is 3p cubed minus 21p squared. That's from the 3p squared being distributed into the 3p and the 3p squared being distributed into the negative 7. And then what I'm going to get is plus 21p squared and then minus 49p. And what we notice is that these two terms are like terms, and they're actually the same thing, just with a positive and negative, so they cancel out, and we end up with just 3p cubed minus 49p. And once again, I'm gonna say, I guarantee you, if you take care of this foiling first and then distribute it in the p, you'll get the exact same answer. Oops, I made a mistake. Sorry about that. This is not a 3p cubed, this is a 9p cubed. My apologies. So it should be a 9p because 3p squared times 3p is 9p cubed. Sorry about that. And on to number 28, which is x plus 1 cubed. Now, just like with the x, what was it? It was x plus 7 squared. We need to take care of this. This is going to be x plus 1 times x plus 1 times x plus 1. It's not going to be x cubed plus 1 cubed. You've got to FOIL. And so from here, you can either FOIL these two things. You can either FOIL these two things first and then FOIL this in, or you can FOIL these two things in and then this. I'm going to opt to take care of this set first. So, distribute it in, and what you get is this x plus 1, this first x plus 1 hasn't gone anywhere, so we're going to keep it there, and then we're going to get x squared plus x plus 1. So the x squared plus x is coming from the x being distributed in, and then the x plus 1 is coming from the 1 being distributed in. And we could now FOIL again here, but it would be better to simplify first. We have these two like terms that can be combined, so we have x plus 1 times x squared plus 2x plus 1. And now we've got to FOIL again. We've got to take the x and distribute it into all three terms. Take the 1 and distribute it into all three terms. And what we end up with is x cubed plus 2x squared plus x. And that's from the x getting distributed in 3 times. Then we're going to get plus x squared plus 2x plus 1, and that's coming from the 1 being distributed in. It's all three terms of the second set. And then we have some like terms. We have the 2x squared and the x squared. and we have the x and the 2x, and those are the only like terms that are present. The x cubed and the 1 here, they have no like terms, so we're just going to have to leave them alone. So this ends up being x cubed plus 3x squared plus 3x plus 1. Number 29 is very similar to this situation. 29 is t minus 3 cubed, and so that's going to be t minus 3 times t minus 3 times t minus 3. And just to show you that you can do it either way, this time I'm going to multiply the first two binomials together first, just to show you that it's no different. It's just a little bit different. The way you approach it's just a slight bit different. So I'm going to FOIL these guys first. And what I end up with is t squared minus 3t minus 3t plus 9, and then t minus 3 is still there because I didn't FOIL this t minus 3 here, so he's still out front. And we see we have a little bit of like terms that can be combined, and we end up with t squared minus 6t plus 9 times t minus 3. And so now we have to distribute. You can either distribute the t minus 3 backwards, or you can distribute the t squared minus 6t plus 9 into the t minus 3. That's what I'm going to do. So I'm going to take this t squared and I'm going to distribute it in. I'm going to take this negative 6t and distribute it in to the second set. And I'm going to take the plus 9 and distribute it in. So I'm going to write these all in color just because it's a little bit confusing when you're writing it all out. So from the green section, from the green distribution, we're going to get t cubed minus 3t squared. From the red distribution, we're going to get minus 6t squared plus 18t. And then from the blue distribution, we're going to get plus 9t minus 27. So, looking at trying to find like terms, we have this 3t squared and this minus 6t squared. Sorry, negative 3t squared and and negative 6t squared. Then we have this plus 18t and this plus 9t, and then the t cubed right here has no like terms, and the minus 27 has no like terms. So we end up with t cubed minus 9t squared plus 27t minus 27. And that is our answer. So it's no different than the 28 and 29 are the same thing. It's just how you go about taking care of the foiling is all that matters. And both ways will work, and both ways will get you full credit on the exam. So 30 now, that is 5t to the 8th plus 5t to the 7th plus 15 divided by 5t. Now, we need to make a distinction between monomial division and polynomial division. Right here, this is monomial division because we've got a polynomial up top divided by a single term, polynomial, so a monomial. So these guys get approached differently. If I had like a plus 7 here, then we've got what we call polynomial division, and we have to use polynomial long division. But monomial, so what we actually have here is this, and the way to approach this is to just divide the 5t into each term. So what we end up with is 5t to the 8th over 5t plus 5t to the 7th over 5t plus 15 over 5t. So here, with this first term, the 5's cancel, and this t cancels just a little bit. It cancels one of the t's. Similarly, the 5's cancel in the second term, and the t cancels just a little bit, and we're left with the 6th power because it cancels out one of the t's. And then on the 15 over 5t, the 5 cancels into the 15 just a little bit, and there's no t that can be canceled, so we end up with t to the 7th plus t to the 6th plus 3 over t. It can be accepted to write it as t to the 7th plus t to the 6th plus 3t to the negative 1, but this is the far more preferred form for this course. We usually like our exponents to be always positive, so that's probably the better way to go about it. So I'm just going to go ahead and even erase this. This is the way we'd like to see you write it if this type of problem shows up on the exam. And so onward to number 31, which is 9x minus 12x squared plus 9x cubed divided by 3x squared. And once again, this is a polynomial up top divided by a singular polynomial, so a monomial. So we're going to do monomial division. This is the same thing as 9x over 3x squared minus 12x squared over 3x squared plus 9x cubed divided by 3x squared. So with this first term, the 3 goes into the 9 3 times, and then the x cancels out one of the x's in the denominator, so we just have a singular x in the denominator. Then with this second term here, the 3 goes into the 12 4 times, and then luckily for us, the x squareds completely cancel each other out. And then on the third term, just like before, the 3 goes into the 9 3 times, but differently, the x squareds cancel out 2 of the x's in the numerator, and we're just left with a singular x up top. So we end up with 3 over x, right? Because there was still one x left in the denominator, minus 4, because in this situation, both x squareds were canceled completely. And then last, 3x, because don't forget about this x to the first power here. So this is our answer. Now we're on to 32, which I'm going to use a new page for. So 32 is m squared minus 2m minus 24 divided by m minus 6. Now the difference between the previous page, so 30 and 31, these were monomial divisions. This one is a polynomial division because we have a binomial here. We have two terms in the denominator. So we're going to have to do polynomial long division. So m minus 6 is our divisor going into our dividend, m squared minus 2m minus 24. And we want to ask ourselves, how many times does m go into m squared? And it goes in m times. So taking the m and multiplying it into the m minus 6, you get m squared minus 6m. And remember, you're going to subtract this. You're going to subtract this entire expression. So we've got m squared minus m squared. So those are going to cancel by design. And then we're going to have negative 2m minus negative 6m. So that's really the same thing as negative 2m plus 4m, which leaves us with a positive 4m. And then we've got to make sure we bring down the minus 24. Now we look at how many times m goes into 4m, and it goes into it positive 4 times. So 4 times m minus 6 gives us 4m minus 24. And once again, we're going to subtract this. So 4m minus 4m, those are going to cancel, and that's by design. And then we're going to have negative 24 minus negative 24, and that's going to cancel. Those are going to cancel out because that's really negative 24 plus 24 because of these two minuses. And so we're going to get a remainder of 0. So our answer is going to be m plus 4 and a remainder of 0. You can use a colon or an equal sign here if you want. Since the remainder is 0, we don't necessarily need to include it, but it's good practice because what if the thing does have an actual remainder that's non-zero? So it's good practice, but you don't have to write it if the remainder is 0. So this is our answer. The next one, which is 33. We have 2a plus 3, and we have 4a squared minus 22a plus 32, and we're dividing that in by 2a plus 3. And once again, this is going to be polynomial long division because we've got a binomial in the denominator, so we can't use monomial division. So our divisor is 2a plus 3, and our dividend is 4a squared minus 22a plus 32. And we ask ourselves, how many times does 2a go into 4a squared? And it goes into it 2a times. So then 2a times 2a plus 3, that'll give us 4a squared plus 6a. And we'll subtract that. So 4a squared minus 4a squared, those are going to cancel, and that's by design. Then we've got a negative 22a minus a positive 6a, so that's negative 22a minus 6a, which gives us negative 28a. And then we've got to make sure we bring down the plus 32. So now what we have to do is we have to ask ourselves, how many times does 2a go into negative 28a? And that would be negative 14 times. And so what we'll end up with is when we take negative 14 and multiply it into 2a plus 3, we're going to get a negative 28a and a negative 42. And then we're going to subtract that. So we have negative 28a minus negative 28a, so that's really negative 28a plus 28a, and so those cancel, and that's by design. And then we have 32 minus a negative 42, so that's really 32 plus 42, which leaves us with 74, which is our remainder. So our answer in this case is our quotient, which is 2a minus 14. That is our quotient right up here. And this is our remainder down here. And so what we write is 2a minus 14, and then remainder is 74. Number 34 is a little bit longer because it's 2r cubed minus 5r squared minus 6r plus 15 divided by r minus 3. So we've got a quadnomial here. There's 4 terms instead of 3 terms up here. But it's going to be done the same way with polynomial long division. So r minus 3 is our divisor. We're going into our dividend, 2r cubed minus 5r squared minus 6r plus 15. And we ask ourselves, how many times does r go into 2r cubed? And it goes into it 2r squared times. And then when we do 2r squared multiplied into r minus 3, we're going to get 2r cubed minus 6r squared, which we will subtract. And the 2r cubes will cancel by design. And then remember once again, this is negative 5r squared minus negative 6r squared. So that's really negative 5r squared plus 6r squared, which ends up leaving us with a positive 1r squared, or just r squared. And then we'll bring down everything else. Next, we ask ourselves, how many times does r go into r squared? And it goes into it r times plus r. And then we're going to multiply r into r minus 3 and write that below it. So that'll be r squared minus 3r. And we'll subtract. And the r squareds will cancel, and that's by design. But then we've got negative 6r minus negative 3r. So that's really negative 6r plus 3r. So we end up with a negative 3r left over. And then we bring down the plus 15. So once again, the reason why it's negative 3r right here is because it's going to be negative 6r minus a negative 3r, which is the same thing as negative 6r plus 3r. And last but not least, we've got to figure out how many times r goes into negative 3r, and it goes into it negative 3 times. And so multiplying r minus 3 by negative 3, we end up with negative 3r plus 9. And we'll subtract that one. And the negative 3r's will cancel by design. And then what we have is 15 minus 9. So we end up with a remainder of 6. So our answer is going to be 2r squared plus r minus 3. That's our quotient with a remainder of 6. And you can write out, I should have mentioned this in the previous ones, but you could write out remainder or you can write r. We'll accept either. On to 35. So 35 is x cubed plus 2x squared minus 3 divided by x minus 1. So this isn't in the previous format that we saw in 32, 33, and 34, but it's the same situation. There's a little bit of a nuance that we need to take care of. The fact is, you'll notice this goes from x cubed to x squared to 3. There's no x term, so we need to take that into account when we're doing the long division. So we're going to write x minus 1, our divisor, into our dividend, x cubed plus 2x squared plus 0x minus 3. It's kind of like a placeholder. We need to have the x to the first power placeholder that I've put right here. So whenever you're missing a power of x in a situation like we are here, so we goes x cubed, x squared, but there's no x to the first term, you've got to make sure you take care of those placeholders. So put a plus 0x there. So how many times does x go into x cubed? It goes into it x squared times. And then x squared times x minus 1 gives us x cubed minus x squared. And if we subtract that, then the x cubes are going to cancel by design, and then we have 2x squared minus negative x squared. So that's really 2x squared plus x squared, so we end up with 3x squared. And we'll bring down the plus 0x and the minus 3. And now we have to ask ourselves, how many times does x go into 3x squared? And it goes into it 3x times. And then we're going to multiply 3x into x minus 1 to get 3x squared minus 3x. And we're going to subtract that. And the 3x squareds will cancel by design. And then we have 0x minus negative 3x, so that should be a positive 3x. And then we'll bring down the minus 3. And last but not least, how many times does x go into 3x? Well, 3 times. So positive 3. And then 3 times x minus 1 gives us 3x minus 3. And when I subtract this, the 3x's cancel by design, and then we have negative 3 minus negative 3, so that's really negative 3 plus 3, and we end up with a remainder of 0. So our answer here is x squared plus 3x plus 3 with a remainder of 0, but once again, if you just want to leave it as x squared plus 3x plus 3 and not write the remainder equals 0, you're totally fine. So, you could write this if you wanted to. But I think it's good practice to write the remainder of 0 there, just in case it doesn't have a remainder of 0. And on to the next one, which is 36, which is a to the 4th minus 1 over a squared plus 1. And once again, this is polynomial long division because our denominator is a binomial, so we can't use monomial division. And the thing to be careful of is this is a to the 4th, but the a cubed, the a squared, and the a terms are not present. So we need to write all the placeholders for those. So this is a squared plus 1 is our divisor, and we're going into a to the 4th plus 0a cubed plus 0a squared plus 0a, then minus 1. I want to make sure you have all your placeholders there because they do play a role. So how many times does a squared go into a to the 4th? Well, it goes into it a squared times. And the reason why, just in case you want to, on a little aside over here, the way I'm figuring that is a to the fourth divided by a squared. I'm taking the leading term of the dividend and dividing by the leading term of the divisor. So if you do this, a squared will cancel just a little bit, and we'll end up with just an a squared. So that's how I'm getting this a squared up top in blue. So now that I have this, a squared into a squared plus 1 gives me a to the fourth, and then a squared times 1 is a positive a squared, so we've got that. There was no a cubed term when I multiplied that in. Subtracting this, the a to the fourths cancel. There was no a cubed term, so these just are gone. And then we've got 0 a squared minus a squared, so that'll be negative 1 a squared or negative a squared. And then I'll bring down the plus 0a and the minus 1. And now I ask myself, how many times does a squared go into negative a squared? And it goes into it negative 1 time. And so negative 1 into a squared minus 1 gives me negative a squared and minus 1. So I'll subtract these. And once again, the a squareds cancel. And then we've got negative 1 minus negative 1. So those actually end up canceling as well. And we end up with a remainder of 0. So our answer is our quotient, which is a squared minus 1. And our remainder is 0, or you could just leave it as a squared minus 1. All right, last polynomial division, so number 37, is y cubed minus 1 over y minus 1. Now, once again, this is polynomial division, and the thing is, there's no y squared term and no y to the first power term, so those placeholders are going to need to be written down when we do the long division. So, y minus 1 is our divisor, and we're dividing that into y cubed plus 0y squared plus 0y minus 1. So the y squared and the y terms need to be, their placeholders need to be there. So, how many times does y go into y cubed? Well, it goes into it y squared times, and then y squared times y minus 1 gives me y cubed minus y squared, and I'll subtract that, and the y cubes will cancel by design, because it's going to be y cubed minus y cubed. Then it's going to be 0y squared minus negative y squared. Those are two minuses here, so that's really 0y squared plus y squared, so we end up with a positive y squared. We'll bring down the plus 0y and the minus 1. And then we're going to ask ourselves, how many times does y go into y squared? And it's going to be y times. So y times y minus 1, you're going to get y squared minus y. And then we're going to subtract that. And the y squareds are going to cancel by design. And just like before, just like above, you've got 0y. It's not exactly like above, but you get the idea. 0y minus y. So minus negative y, so it's going to really be adding y, so we've got y minus 1. And last but not least, how many times does y go into y? Well, it goes into it 1 time. So positive 1, multiplying 1 into y minus 1, you're going to get y minus 1, and when we subtract this, we're going to get the y's cancel, and also the negative 1s will cancel, because it's going to be negative 1 minus negative 1, which will give us a remainder of 0. So our answer here is going to be y squared plus y plus 1 with a remainder of 0, or you can just leave off the remainder if the remainder is 0. And now we're on to part 3, which is to solve each of the systems of linear equations by substitution and or elimination. Now, with each one of these ones, I'm going to choose the one that I find to be the best in each scenario. But do know that you can use whichever method you want. you're not required to do one over the other. It's just which one will work best in each given scenario. So, 38. And I'll tell you why I'm choosing the one I am. So the system is x equals 3y minus 1 and 2x minus 4y equals 2. Now, looking at this one, I'm going to use substitution, the substitution method. And the reason why I'm going to do that is because x has already been given in terms of y in this first equation. So all I really need to do is take this and plug this in for x in the second equation, because x is already given to me in the first equation as 3y minus 1. So this will lead me to 2 times 3y minus 1, because it was 2x, and I'm going to replace x with 3y minus 1, and then continue on, minus 4y equals 2. We've got to distribute in that 2, and we end up with 6y minus 2 minus 4y equals 2. And we're going to solve this linear equation like normal. There's two like terms. We're going to get 2y minus 2 equals 2. We're going to add 2 to both sides to cancel out these 2's. We've got 2y equals 4. And then we're going to divide both sides by 2 to get that y is equal to 2. Now I can plug this value right back into this original equation right here to find what x is, because x is equal to 3y minus 1. So, if x is equal to 3y minus 1 and y is equal to 2, this gives us that x is equal to 3 times 2 minus 1, which is 5. So x is equal to 5 and y is equal to 2, which means that our answer is 5, 2. We'll accept it if you write it as x equals 5 and y equals 2, like what I have here, but preferably you'd like to write it as an ordered pair to think about these things geometrically. So these are two lines, and so they intersect at a coordinate point, 5, 2. Now, one of the best parts about these problems, if these show up on the exam, is you can always check your work. You can always make sure that you're actually getting the right answer. And the way to do that is to take this point and plug it into both equations. If you're strapped for time, maybe just plug it into one of them, but ideally plug it into two. Plug it into both of them. So, because if I plug in 5 for x here and 2 for y here, I'm going to get 10 minus 8, and that'll equal 2. So that creates a true statement, so it is a solution to this one. And since I can do it here too and show that it is a solution for this first equation as well, so I know that I got the right answer. If I plug this in and I don't get a true statement, then I know I made a mistake somewhere, and I should look through all my work to figure out where I went wrong, where I made a mistake. So, 39. 39 is, the system is 2x plus 4 equals 2y, and y minus x is equal to negative 3. Personally, I'd like to, I think both elimination, or like the substitution and or addition method would work in either case here, purely because of the coefficients. I'm going to go ahead and do elimination, just because I like elimination more, but I want to make sure we notice something. The 2y is over here on this one, and the constant is on the left, so we want to bring the 2y over and the 4 to the right. And then secondly, on this second equation, notice that it goes y then x, and that's a good way to get yourself confused, so make sure you arrange it the correct way. So with this first equation, so off on the side here, 2x plus 4 equals 2y. If I subtract 2y from both sides, I'll get 2x minus 2y plus 4 equals 0, and then I want to get rid of, I want to bring the 4 to the other side, and so I'll have 2x minus 2y is equal to negative 4. So that's with regards to this equation. That's the better way to write it. And then with the y minus x, I'm just going to rewrite it as negative x plus y equals negative 3. I'm going to or reorganize the terms, because this is a minus x or a negative x, and this is a positive y, so plus y, and then the negative 3 is still the negative 3. So rewriting the system, we've got 2x minus 2y equals negative 4, and negative x plus y equals negative 3. So I'm going to go ahead and get rid of the x term, and so I need to multiply the second equation, the bottom equation, by 2 so that I get the x terms to have the same coefficient. So I'm going to multiply the entire equation. Remember, you have to multiply the entire equation. A very common mistake students make is only multiplying the left half, but you still have to distribute into this too. So this becomes 2x minus 2y equals negative 4, and then we've got negative 2x plus 2y equals negative 6. And now I'm going to add these two expressions together. We've got 2x plus negative 2x. Those are going to cancel. And then we've got negative 2y plus 2y. So those are also going to cancel. So on the left-hand side, all I have is 0. And then on the right-hand side, negative 4 plus negative 6, that's equal to negative 10. So we have 0 equals negative 10. Now this right here, this is a false statement. And when you're solving systems of equations, linear equations, and you run into a false statement like I just did here, that means that there is no solution. Because just like with regular linear equations, if you end up getting like 0 equals 5 or negative 1 equals 10 or something like that, that means that there's no solution because it's not a true statement. Whenever this happens, I'm usually a little skeptical, so I would always recommend if you run into this situation where you get a false statement, I would definitely go back and check all your work and make sure everything is correct. If you have time, of course. Like I have checked my work, and this is actually the answer. So because I got a false statement, there is no solution. On to 40, which is the system x minus 2y equals 4, and 2x plus y equals negative 2. Now, I would argue that addition method and the substitution method would be perfect candidates for this one, purely because in the first equation, you could solve for x in terms of y by just adding 2y to both sides, or you could have, in the second equation, you could subtract 2x to solve for y in terms of x. So either method is fine, and since I did elimination last time, I'm going to do substitution here. So by adding 2y to both sides of this one, I'll get that x is equal to 2y plus 4. And I'm going to substitute this in to the second equation for x, and I'll get 2 times 2y plus 4 plus, that looks like, right here, it looks like a plus y, or a 7y, so plus y. Plus y equals negative 2. Remembering to distribute the 2 in, but not distributing it into the y because that's not part of the parentheses. We're going to get 4y plus 8 plus y equals negative 2, which simplifies to 5y plus 8 equals negative 2, and I'll subtract 8 from both sides. Cancel the 8s. I get 5y is equal to negative 10. At which point I'm going to divide both sides by 5 and get that y is equal to negative 2. So that's our value for y, and what I'm going to do is I'm just going to plug that in for y right up here to solve for x. Because we're not done yet. We need to find out what x is. So because of this, wrong color, x is going to equal 2 times negative 2 plus 4, because y is negative 2, and you get that x is equal to 0. So our answer is x equals 0, and y equals negative 2, or preferably 0, negative 2, our coordinate point, x, y. So x is 0, so that's why it's 0, y, which is negative 2. And last one. 41 is the system 5x minus 2y equals 6, and negative 5 halves x plus y equals 5. Now to start off with, I don't like dealing with fractions. So what I'm going to do, so the first equation is all in integers, and that's going to be fine. However, this second equation has this fraction here, so I'm going to multiply this entire equation, not just the left. I need to do it to both sides. I'm going to multiply it by the LCD, which in this case is 2. So I'm going to distribute this in. You're going to get a new system, 5x minus 2y equals 6, and then when I distribute the 2 into the negative 5 halves x, I'll get a negative 5x, and then plus 2y equals 10. And luckily for us, addition method seems perfect for this one, purely because the x terms, and in fact also the y terms, they have the same coefficient. So since this is 5x and this is negative 5x, I'm just going to add these two equations together. And then 5x plus negative 5x, those cancel. Negative 2y plus 2y, that's also going to cancel. That's not good. Well, it's not good, but it's just weird. And then 6 plus 10, that's 16. So on the left, there was nothing left. So we have 0 equals 16. And once again, we've run into a false statement. We run into a false statement, which means that there is no solution. As I said before, you always want to check your work with. If you come to the conclusion that that there's no solution, you should definitely make sure that you did your algebra correct. Another thing you could do if you wanted to verify your answer is to see if these are parallel lines. If you rewrite these in the form y equals mx plus b, if they have the same slope but different y-intercepts, they're parallel and they'll never intersect, which means that there is no solution. So that's another way you could do this to verify your answer. And that is it for the exam for review solutions. Thank you.